All right, grade 12 SL. We're going to be doing moving from electric fields into electric potential and voltage, stuff that you've seen when you look at batteries. And what we're going to try to do in this little video is to first understand how charges can store electrical energy, okay, the energy that's causing this guy to zap and move. All right, then we're going to define the term electrical potential, and then we're going to understand what the unit volt means, okay, on your batteries. And we're going to learn how to use volts when calculating energy of charged particles in electric fields. Okay, it seems like a lot, but it's actually not much. Okay, so if we take a look at this little squirrel, when it bites into a power cord, it experiences an electrical shock, and maybe some of you have experienced that as well. And that's because at that moment, when he attaches himself to that wire, this side of that squirrel's body is experiencing a higher voltage than that side. What it is experiencing is something called a potential difference. And with that potential difference, charges will move. And when the charges move, they release electrical energy, causing that buzzing sensation or your muscles to contract or even burning. Okay? So electrical potential and electrical potential difference is how we calculate the energy associated with electrical charges. And that's the big idea for this lesson. How do we calculate the energy associated with the movement of charge? So first of all, in order to answer that, we got to figure out how can a charge even store electrical energy, okay? And that goes back to our original diagram. So here I've charged a sphere with positive 1 coulomb using Arnav's inductive charging. We've made it positive 1 coulomb. And if I take a small test charge at a distance that is, let's say, an infinite distance away, at an infinite distance, that charged particle is barely feeling any force from that positive 1 coulomb charge. But then if I come in, okay, and I take my finger, okay, and I push that charge towards this object, that charge is going to start to experience a force, okay? And if I was to graph that force as I'm over here at that distance, that force is going to become exponentially large. Okay, r would be the radius, okay? And we know that from Coulomb's law, F is equal to K Q1 Q2 over r. So I'd be able to see that as I'm pushing that charge towards this object, the force is going to go up exponentially. And then how does that relate to energy? Well, in order for me to move that charge, I'm going to have to do work, okay? And remember that work is equal to force times distance. So if I am walking it over a distance of r, okay, and I'm able to map the force that is moving up, and I'm able to map the distance that I'm moving, if I multiply that force by the distance and get this area under the graph, that would tell me the total work that I put into moving that charge to, let's say, this point over here, point P. Okay, so if I'm able to calculate the work, where does that work go? Well, that work, just like when we talked about conservation of energy, the work that I put in is going to be stored as electrical potential energy. Okay, that's the energy associated with the electrical field, okay? Moving a charge, making it do work due to repulsion. So the force it's experiencing is the Coulomb's force. Moving at a distance, that force times distance will tell me the work that I did, which is equal to my electrical potential energy. So what can that electrical potential energy do once it's stored here? Well, that electrical potential energy can be converted into other things, such as the kinetic energy. When I release it, that charge can fly out, and it'll be converted back into kinetic energy. Or it can be converted into heat and light, which we're going to see later on. Okay, so that's in a very visual explanation how a charge can store energy. So when I push the charge, and if I kept my finger there, that charge will have electrical potential energy. And then if I let go of my finger, that charge is going to fly in that direction. Okay, so we have to have a mechanism to store that charge there, to hold it there. Okay, otherwise it's going to release that electrical potential energy. Okay, so let's just erase this. Okay, we know that the work is equal to force times distance. So let's see if we can come up with a formula. Is there a formula for electric potential energy? Let's see if we can derive that. This is a really cool thing to do. Okay, so using our general formula of work is equal to force times distance, okay, work is equal to force times distance. If I plug in for force Coulomb's law, okay, let's see if we can do that. I'm just gonna do that over here to the right. So if I plug in the work, electrical potential energy is equal to K Q1 Q2 over R squared, and R is the distance. So I can make this R, distance, times R, okay? That will end up canceling out one of those R's. So we've created an equation where work is equal to K Q1 Q2 over R. That is an equation for our electrical potential energy. So if I knew the magnitude of the charge, I knew the magnitude of the other charge, and I know the distance, let's say that that's 1 meter, okay, I would be able to calculate how much electrical potential energy a charge would have at any point in time using this formula. So you might want to pause this video and write that formula down. You do have these formulas in your data booklet, but definitely write that down. That's a good formula. And it's slightly different than this formula, which was for force. So take a look and see if you understand that relationship. Work times distance is, sorry, not work times distance, force times distance is work. Okay, and that's where it comes from. So if I remove one of those R's, it now becomes electrical potential energy. So what is the definition in a nutshell? If I had to derive this on an exam, I would say it's the work done moving a charge from an infinite distance to a specific point in an electric field. That's what we just described in this picture above. Okay, that is the definition. You have to remember that. Okay, so electrical potential energy is the work done, not energy stored. It's the work done moving a charge from an infinite distance to a specific point in an electric field. Okay, and it's calculated using that formula right over here. Okay, next question. So what is the definition of electric potential? Notice that this is different than electrical potential energy. It's missing energy. So what is electric potential? A lot of students get confused. Okay, so electrical potential is not the same as electrical potential energy. And what electrical potential is, it's the work done per unit charge. So I can underline that. Okay, it's the work done per unit charge, moving a test charge from an infinite distance to a point in an electric field. Okay, so if I had a positive charge, okay, and I move it slowly towards that positive 1 Coulomb charge, it's gonna, I have to do work to move it there, okay? And if I took it to this point and I divided it by the charge of this particle, I would get something called electrical potential. So let's move it over here. So electric potential at this point, at point P, according to the definition, is the energy or the work that I did divided by the charge of the particle, okay, which is equal to joules per Coulomb, which is equal to joules per Coulomb. Okay, so that's electrical potential. Electrical potential energy is just joules. Okay, so what is the meaning of this joules per Coulomb? Well, that basically means, I'm just going to erase this part here. That basically means that if I move any charged object, this can be a proton or this can be a spaceship, okay, a spaceship that has positive 1 million coulombs. If I move either of those objects to that point, they both will have the same electrical potential. Okay, the work that I did divided by the total number of charges would yield the same electrical potential. For example, positive 1,000 joules per Coulomb, okay, which is equal to 1,000 volts. Okay, the term volts. The term volt is electrical potential. Joules per Coulomb is just another way of remembering that. So whenever I see volts, I see joules per Coulomb. Okay, so this line that you see over here, that fixed distance r of that charge and that central charged object, that distance r, anything that is along that radius, if I drew a circle with that radius, anything that is along that radius is going to have the same electrical potential. That means that any object there has 1,000 joules of energy per unit of charge that it has. This spaceship would have 1,000 volts. This proton would have 1,000 volts if it's sitting there. But what they do not have is the same amount of energy. They're sitting at the same electrical potential, but they don't have the same amount of energy. Without a doubt, at 1,000 volts or 1,000 joules per coulomb at that point, the spaceship with 1,000,000 coulombs is going to have a lot more electrical potential energy than a measly proton that has 1.6 times 10 to the minus 19 coulombs. Okay, and I'm going to show you how I would calculate that later on. So this object has a lot more energy than that object. But at this point, they have 1,000 joules. They both have 1,000 volts. They're sitting at the same electrical potential. Okay, and if they moved to a point over here, that point is further away. Okay, so question for yourself. Would you think that the electrical potential, the amount of energy per charge at this point, would that be greater or less than this point? What do you think? Okay, well, at this point, we can say, oh, it's much further away, but it has a 10 volt potential, or 10 joules per coulomb. Okay, at that point. So if you take a look at that, the electric potential as I get further and further away becomes very, very, very small. So how can I create a formula for electrical potential? Okay, well, using the definition, it's the work done per unit charge of the moving charge. Okay, so if I take a look, I'm just going to erase this stuff over here to see if we can come up with the equation. Okay, so work, according to the last equation, was Q1 Q2 over R. So in order to turn this formula into the definition for electrical potential, I got to get it to joules per coulomb. So which of these charges do I move? Imagine that's Q1 and that's Q2. Well, Q2 is the moving object, so I'd have to move Q2 over to this side. So in order to get volts, okay, which is work over charge, it's going to be Q1 over R. And you have this equation in your data booklet. Okay, so try to find these equations in your data booklet. So that's what voltage means. So the voltage at a specific point, the electrical potential, is equal to K, Coulomb's constant, times Q1, the central object creating an electrical field, divided by any distance around it. So I could be able to calculate any voltage around that object, and I can map it out. Okay. Once I use this formula, I can create something called equipotential lines. So if I have a positively charged object that is emanating a field, okay, this is our field diagram if you remember. So it's emanating a field. What I can say is if I draw these concentric rings around that with a fixed radius, imagine that's a perfect circle. Probably could have done that using a different tool, but it's okay. So these concentric circles are called equipotential surfaces or lines. Okay, and those equipotential surfaces mean that at that surface, if I follow that arc, if I follow that circumference, the radius is always the same. Okay, so if the radius of that circle is always the same, that means the voltage experienced over there, let's say that that's 10 volts, let's say that this is 1,000 volts, and let's say that this is 10,000 volts, okay? The voltage or the electrical potential at that point in space is always going to be the same. And if I move closer, now my electrical potential gets higher. And then if I moved even closer, it gets higher. Now notice that for the same distance, okay, it changes quite dramatically, okay? So because it's inversely proportional, okay? So it's not a linear trend, it's a inversely proportional trend, okay? So the next question is, if I was a charge over here and I moved to this point, how would I be able to use the voltages to calculate how much work I had to do or energy that I had to put in to take a charge from here and move it to here, or to take a charge from here and move it to there? Okay, so how do I use voltage or potential difference to calculate the energy changes in the movement of charged particles? So from here to there, okay? Well, that's quite simple, okay? So let's just blow this up. So if I had two equipotential lines, and here I am a positive 1 coulomb. Yeah, let's make it positive 0.1 coulomb charge. Okay, and I want to move to that point, and let's say that this is 10 volts, and this is 100 volts. Okay, what I would need to do is I would need to find out the potential difference. Okay, so what's the difference between 10 volts and 100 volts? Well, the difference, so the PD, which is potential difference, is going to be 100 volts minus 10 volts, which is going to be 90 volts. Or another way of saying volts, if you remember, is 90 joules per coulomb. So how would I use 90 joules per coulomb and that charge to be able to find energy? So just take a look at the units. How would you use that and that to be able to find the energy that I have to put in to move that charge from here to there? So I'd have to put in energy. Well, if you looked at it, you would say, okay, well, the energy is going to be equal to my voltage difference, the potential difference, this, times the charge of this particle. Okay, so then the energy is equal to 90 joules per coulomb times 0.1. My energy that I would have to put in is equal to 9 joules. Okay, 9 joules. All right, that seems pretty basic. So let's just do one simple question before in the next video I'll do a bunch more practice problems so you can see how you can apply voltage and potential difference to calculate energy. But here's a good practical problem. Calculate the kinetic energy of a proton that moves from an electrical potential of 1000 volts to an electrical potential of 100 volts. Let's try to figure out why there's kinetic energy. So here's my two potentials. Okay, this is positive 1000 volts and this is positive 100 volts. Okay, and now I have a charged particle that is over there, and that's a proton. Okay, and that proton is released. I lifted my finger, and it flies to that point over there. So remember, the potential difference is equal to 1000 volts minus 100 volts. So I'll have a total potential difference of 900 volts, okay, or 900 joules per coulomb, okay, is the potential difference. All right, so if I wanted to calculate the energy released at this point, it's at a higher potential. So this object has high electrical potential energy. Okay, you can think that it's like, for example, when we talked about gravitational potential energy, you can think that this is the roller coaster that is uphill. It has higher energy. And when it falls down, it's going to release that energy in the form of kinetic energy. It's going to not release it, it's going to transform it into kinetic energy. So this would be like potential energy, and then this would be kinetic energy. And the same thing here. It's going to go from high electrical potential energy to a lower, okay, so this is low, okay, so uphill to downhill. And then that energy is going to be transformed into kinetic energy. So whatever energy I find associated with that potential difference in that proton, that potential difference in the energy there is going to go to kinetic energy. So then I can say that the potential energy is going to be converted into kinetic energy. So in order to calculate the potential energy, I would take 900 joules per coulomb times the charge of a proton, which is 1.6 times 10 to the minus 19 coulombs. And once I multiply those together, that would give me the total kinetic energy that I have for that proton. And I can probably predict that the next question would be to calculate the velocity. So if I wanted to calculate the velocity, I would then use that kinetic energy, and I would say Ke is equal to 1/2 mv squared. So in order to do that, I need to know the mass of my proton, okay, and I would use this equation to then calculate the velocity that that proton has at that point. And that's it.